Hey, welcome back to chemistry, and now we're moving into a new chapter, which is entitled Chemical Reactions in Aqueous Solutions. Okay, so what I first want to go over is I want to understand a little bit about the basics of what chemical equations look like and why we balance them. So you may already know what balancing a chemical equation is. That's the point where you write out formulas for an equation and then you throw in numbers in front of the formulas to balance the number of atoms. And so first, before we start doing that, and I'll do that at the end of this presentation, I want to talk a little bit about why we do that. So let me just kind of give you an example of a chemical reaction, which we're going to kind of go over in some gory detail. And so this is kind of an interesting chemical reaction. So you can, as you know, burn natural gas. And so there's sort of a picture there on the right of natural gas burning. And so the device it's burning from, you may have already seen in the past, is something called a Bunsen burner. So you might wonder what natural gas is. And natural gas is made of a pure substance. It's a chemical called methane. And so there's a picture of the methane molecule. And so it has one carbon atom in the center, and then there are 4 hydrogen atoms that are stuck to it. So one thing that's kind of interesting is if you tried to burn natural gas in an environment that had only nitrogen and nothing else, you would not be able to ignite the natural gas. It just would not burn. It would not combust. So what that might tell you is for natural gas to burn, there must be something else in air other than nitrogen that is required for the reaction. And that thing is oxygen. So oxygen is also required for the reaction. However, when the oxygen meets with the methane and there's something to start the reaction like a little bit of flame, they will completely react. And so what will happen is when they completely react, they're gone. They completely disappear. And so those things that disappear in the reaction that you had before are said to be the reactants. Now, what will happen is the reason why they disappear is because in that flame, the oxygen will meet up with the methane molecule. And although the total atoms are still there, they tend to rearrange themselves and they reform new molecules. And the new molecules that they form are carbon dioxide and water. And so these are the products of the reaction. So what we can kind of do is sort of describe the burning of natural gas. You can also call it the combustion of natural gas with this equation. And so I've written out the equation in sort of 2 ways. I've written it out in sort of pictorial form, which kind of helps me out in understanding it. And also I've written it out in terms of the names of the molecules and their formulas. And so what I've done is I'm showing it looks like we're having methane reacting with oxygen. Those are the reactants, and they will produce carbon dioxide in the water. And as you probably already know, the methane, the oxygen, which are to the left of the arrow, will be the reactants of the reaction. And the carbon dioxide in the water, which are to the right of the arrow, are the products of the reaction. So one thing you might want to check for, based on what we already kind of know is the law of conservation of mass, we might want to confirm that the number of atoms for each element is the same whether it's reactants or products, because for really reactions to completely go, we need that requirement. So let's go ahead and do that. So what I've done is I counted up the atoms of each of the elements on the reactant side and then on the product side. So for example, you can see with carbon, that black element, there's 1 on the reactant side and there's 1 on the product side. So that's a good sign. Now, if you look at hydrogen, there are 4 of those white atoms, the hydrogen atoms, on the reactant side, but on the product side, there are only 2, so that may be a bit of a problem. And with oxygen on the reactant side, those 2 red atoms, there's 2 oxygens, but you can see that now in the products, another one seems to have appeared. There are 3 oxygen atoms. So something weird has happened. We really don't have atom balance on the left side versus the right side of the equation. And so it's almost as if, as it's written, that we are actually having hydrogens just kind of disappearing and going off somewhere. And also maybe oxygens are just appearing from nowhere. And so that can't happen. So this doesn't seem to make sense to us. So there's still something not quite right with writing this equation in this way. And so what we may want to do is change the proportions of molecules that are reacting such that the atoms for each element are equal on the left side versus the right side of the equation. And so again, I sort of indicated here that as the equation is written with one apiece, and you can see it's written in different ways. We're showing it's written, these pure substances are written out as words at the top, and then we have an equation with formulas, and then we have pictures. And so what this is a good qualitative description of the chemical reaction, because what a qualitative description is about is it tells you the kinds of molecules that are reacting and the kinds of molecules that are being produced, but it doesn't really have any numbers associated with the description. So this is a reasonably good qualitative description. But the problem is this is not a good quantitative description for the problems that we saw before. We don't right now, as things are written, have the correct proportions of these molecules that are reacting. Now, we can change it pretty simply. So if we add in another oxygen molecule as a reactant, and we add in another water molecule as a product, then it becomes not only a good qualitative description, but a good quantitative description of the reaction. So let me talk about why it's a good quantitative description. So the reason why is, remember beforehand when we had one of each and we didn't really have good atom balance for the elements? Now, then we added an oxygen molecule and a water molecule. What you can sort of see is that for each element, there are as many atoms of that element on the reactant side as you see on the product side. And so for carbon, for example, we're still good with one carbon atom in methane and one carbon atom in carbon dioxide. So we have carbon balance on either side of the arrow. Now let's look at hydrogens. When we added that extra water as a product, we now have a total of 4 hydrogen atoms in the product, which matches the 4 hydrogen atoms in the methane molecule in the reactant. So the hydrogens now balance. Also, when we added that extra oxygen into the equation, now we have oxygen balance. On both sides of the arrow, we have 4 oxygen atoms. And so basically we have a balanced equation. So how do we balance the equation? We just added additional molecules as necessary so that we got atom balance for each of the elements. When you add additional molecules for a particular compound, then you're changing the number of molecules involved in the reaction, and therefore you would change the coefficient in front of the formula. So let's talk about that now. So when we have good quantitative balance of the atoms, that is sort of the ratio of the molecules that are reacting. So it's not 1-to-1 produces 1-to-1. We now realize that for the law of conservation of mass to be satisfied, we really need 2 of oxygen reacting with 1 of methane to produce 2 of water and 1 of carbon dioxide. Now, you could just add molecules to that. So again, 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Now, one of the things that we've learned is that there is a direct relationship between moles of a substance and a molecule of a substance. So what you can also say, because moles and molecules are directly related, that 1 mole of methane will react with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. And so what we can do now is write a final equation using formulas. And note what I've done. I've indicated the mole ratios with the coefficients. And so the reason why you don't see a coefficient in front of methane, which is CH4, if you don't see a coefficient there, assume the coefficient is 1. So there's really a 1 there. Also, beside carbon dioxide, there's really 1 there. Okay. And so the coefficients you can see a reference to either the mole proportions of these molecules or the molecule proportions of the molecules. Okay, so I kind of already mentioned that. So one question you can kind of ask yourself is the following. Would it be true to say that 1 gram of methane will react with 2 grams of oxygen to produce 1 gram of carbon dioxide and 2 grams of water? And the answer is no. Those proportions are only good for molecules and moles. They will not work for grams, and that's important to know. However, if you want to know what the proportions of grams are for these molecules that are reacting and that are produced, it's pretty easy to take the moles of each molecule and figure out the grams involved for each molecule. And all you have to do is take those numbers and then convert them to grams using the molar mass. The molar mass tells you for each molecule how many grams of molecule are there with that mole of that molecule. So for example, methane, you can work out the molar mass of methane, and it's 16.02 grams of methane per mole. With diatomic oxygen, O2, it's 32 grams of oxygen per mole. Carbon dioxide is 44 grams carbon dioxide per mole, and then water is 18.01 grams per mole. Now, what you can do is take those molar masses and multiply them by the moles, and let's see, given this reaction, what are the masses that react? Well, if you do that, you can see that you get those numbers, which I'm showing you on the screen, and as it turns out, you have 80.02 grams of reactants, and then you also have 80.02 grams of products, and so we have a really nice mass balance here. So I think you can sort of see at this point why you need the balance equations. In other words, why do you need to put coefficients in front of those formulas? And the reason is once you do that, you get atom balance on the left side of the equation versus the right side of the equation for each element, but then you also get mass balance if you convert those moles into grams using the molar mass. So that's why you use those coefficients.